G'day, I'm James, and today I'd like to talk about a particular topic in the curriculum which I think we've over-cluttered and have lost sight of the beautiful natural story it offers. Is this one, proportional reasoning, often called ratio proportions or ratios proportional relationships, some word involving proportional at some point in the title. Proportional reasoning. And what we're actually doing here is actually denying our students the invitation to be confident 21st century citizens, namely to rely on their own wits and have the confidence to solve problems just by following their noses and using their fabulous brains. We've made this topic too cluttered. And to illustrate what I mean by that, I'm going to take a typical textbook problem, one like this one, and show how we can actually work our way through it without knowing anything, without any of the words, without any of the jargon, without any of the constructs that we often make our students do. Just do it. Just do the topic. So it's this one. I'll take this example here. Now, it's about these things. Emu eggs. I'm going to have an emu egg. Apparently, I can make 1,200 omelets with 15 of these things, with 15 emu eggs. Part A of this question. How many omelets can I make with 100 eggs then? Or 20 eggs? Or 464 eggs? Or 9,872 eggs? Great. Part B, other way around. Actually, I need 200 omelets. So the question is, how many eggs will I need for a fixed number of omelets? Namely, 200 of them. Okay, so a textbook might not be about emu eggs per se, but this is very typical of a textbook problem in this particular topic. Now, right now, we've talked about nothing. Talked about nothing about this topic, but I bet your students and we, right now, can answer this just by using common sense. And that's what I want to teach the next generation, how to rely on their common sense to make progress with problems. Great. All right, but I will analyze this for us, because what's really going on here are just 4 key points. Number 1, I have a scenario here that has 2 quantities in it, namely a count of omelets and a count of eggs. That is, I can actually measure the number of omelets and measure the number of eggs. So point number 1, there are 2 quantities in here that I can measure. Great. Second, these quantities vary, because I can imagine making different number of omelets using different number of eggs. So these quantities have different values. They have varying values. It's a dynamic situation, not a static one, not just like one particular number of eggs and one particular number of omelets. It can vary. In fact, we do. We want varying number of eggs. I guess we're going to get varying number of omelets. So point number 2, we've got 2 measurable quantities whose values can vary. All right, point number 3. They actually seem to be related to each other. That actually the number of omelets you make depends on the number of eggs. The number of eggs you need depends on the number of omelets you want, and so on. So they actually these 2 quantities actually depend on each other in some way. Great, that's point number 3. We've got 2 measurable quantities whose values can vary, but their values seem to depend on each other. And then there's the 4th key point. But let me play with it. Let me play with these numbers. So let me start the problem before I get to the 4th point. So right now, I know I can make 1,200 omelets with 15 eggs. So with 15 eggs, I'll focus on eggs. I'll make that my sort of driving force here. I can get to that 1,200 omelets. So now, I just made up notation there. I made double arrows. It means like goes with, like 15 eggs goes with 1,200 omelets. Some people might want to write an equal sign, or some people might want to do a table. Whatever you want to do is fine. But in the end, I have to associate the number 15 eggs with the quantity 15 eggs with the quantity 1,200 omelets. Okay, so I'm just going to use double arrows, why not? But now I'm going to rely on common sense, my real world experience, because my real world says, oh, if I doubled the number of eggs, made that 30 eggs, then I know I'll be able to make double the number of omelets. That's just real world common sense. Omelets, there we go. Beautiful, double the number of eggs, double the number of omelets. Actually, if I divide the number of omelets by 10, if I want to make 240 omelets, I can actually go the other way. If I did 1/10 the number of omelets, I guess I'll need 1/10 the number of eggs. Oh, beautiful. If I did 1/3 of the number of eggs, I guess I'll get 1/3 of the count of omelets. Yes, 80 omelets. Beautiful, beautiful. And if I say tenfold this, tenfold the number of eggs, I'll get tenfold the number of omelets. And off I go. I can actually keep doing this over and over again and have a grand old time. Varying the number of eggs, varying the number of omelets, or vice versa. Beautiful. But what I'm noticing here, that these 2 varying quantities that I can measure actually scale in tandem. In fact, this is my favorite term here, scale in tandem. I wish the books would use this. They scale in tandem. What I mean by that, if I double one quantity, the other quantity doubles. If I triple one quantity, the other quantity triples. If I halve one quantity, the other quantity halves. If I do 1/3 of one quantity, well, that other quantity goes to 1/3. If I 100-fold a quantity, the other quantity 100-folds. They scale together. If I change one quantity by a scale factor 74, the other one changes by a scale factor 74 as well. Bingo, that's it. That's given the name proportional reasoning. Two things that scale in tandem. So I have a scenario. First of all, one, it's got two quantities that I can measure. Two, those quantities can vary in value. I can imagine they do, or they actually do. Three, they seem to depend on each other. Yep, they do. But most important, the fourth point, four. How do you do four? Four, that way. Fourth point is, I've got two quantities that scale in tandem. That's it. Once you recognize you're in a scenario like that, common sense leads the way. In fact, let's now go answer the textbook problem. What have I got going on here? 1,200 omelets for 15 eggs. Yep, 15 eggs goes with 1,200 omelets. And then I can just keep adjusting the numbers. Oh, I can keep adjusting the numbers any way I want. What do I want? I want 100 eggs. Oh, there's 10 eggs was 80 omelets. So I guess 100 eggs is 8,000 omelets. Whoops, whoops, whoops. 8,000 omelets. If I can only write correctly. So tenfold, tenfold. There we go. 10 times 10 is 100. 800 times 10 is 8,000 omelets. Bingo, done that one. 20 eggs, 20 eggs. Oh, okay, 20 eggs, I can just double this one. Double 10 eggs must give me double the number of omelets, 1,600 omelets. Oh my goodness, it's just all falling into place. Ooh, 464 eggs. Ooh, that's awkward. Ooh, oh, actually, let me go to this line. I like this line. Because I've got one egg gives me 80 omelets. So if I want 464 eggs, let's just multiply by a factor of 464. 64 eggs must go with 80 times 464 omelets, whatever that number is. I'll have to get out my calculator for that one, but that's fine. I can work it out. In fact, I can work out 9,872 eggs. Multiply this by 9872. Therefore, I must multiply that by 9872 and work it out my calculator. I can actually solve that. That is fine. That's beautiful. In fact, this line is beautiful. And once you've got one egg, it kind of unlocks everything. In fact, I can do any number of eggs now. Let me just give myself a little bit of space. If I want to be a little more algebraic and say, okay, what if I had n eggs? N eggs? That is, I just take this one and multiply by a factor of n, means my answer, number of omelets, must be multiplied by a factor of n. Must give me 80 times n omelets. In fact, if in an algebra class, I now have an algebraic equation that the number of omelets is 80 times n, where n equals the number of eggs. And how's that for very bad handwriting? But hopefully you heard what I said. The number of omelets is 80n, where n is the number of eggs. Beautiful. Great, because that means I can now just answer this any way I like. Now, part B, I want 200 omelets. Rather than just the number of eggs, I now want to adjust the number of omelets. So what can I do here? Actually I can go to this one if you like, and say, 800 omelets is 10 eggs. What if I divided this by 4? Which case I need 10 divided by 4 eggs. 10 divided by 4, that's 5 divided, that's 2.5 eggs. Bingo, I know how to solve that one. Or if you like, you want to be a little more algebraic, if you're in upper grades, 200 equals 80n, therefore n must be 200 over 80. The number of eggs must be 200 over 80, which is 20 over 8, which is 10 over 4, which is 2.5. Beautiful, beautiful. We've done it all. We've done it all. This is the typical problem in a textbook, and common sense leads the way. Common sense leads the way. So, beautiful. Now, of course, the key thing here is notice that once you've got one egg, you kind of got everything. So people give this a name. They call this the unit rate or something, or the rate. 80 omelets for one egg. Okay, sure. Or just go for one egg and your life is easier. Or you might be focusing on the number of omelets, which is go for one omelet and get a unit rate in terms of eggs or something instead. Either way is good. There's two ways to think about rates here. Depends if you want to focus on the eggs first or focus on the omelets first. Depends on what the question's about. Gran. Now, what I want to do is just write up on the board right now the key points, those 4 things I point about what makes this a proportional relationship problem, because once you got that, it's just the same common sense over and over again. Write down your first statement, 15 eggs goes with 1,200 omelets, and just scale in tandem to your heart's content, and you can answer everything about that question. Everything. What makes it tricky is the curriculum, as I pointed out, wants to introduce lots of jargon and lots of strange techniques to represent this. They'll use the word like unit rate. They might have you not draw double arrows like I do, make you do tables, and they might want you to notice patterns in tables all over the place. They might want you to draw these things called double number lines. They'll start having you graphing data. They might start saying, notice all the data seems to go through a line through the origin, which makes sense because every line is basically y equals kx or something like that. So advanced algebra gets very deep here for reasons that are just not really needed because it's just a simple idea. Just scale in tandem, scale in tandem. All right, so I will go through all the peripheral stuff that's in the curriculum in other videos, but what I want to do next is clean the board, write down the 4 key points we're looking for, and just practice identifying, do we have scenarios with those 4 key points? If the answer is yes, scale in tandem to your heart's content, and everything will fall into place. If the answer is no, you have to do something else, have to figure out something else that your clever brain can do, and I bet your brains can do it too. All right, so I'll clean the board and back in a moment. So you're in a scenario, and to look for a proportional relationship, all you have to do is ask yourself the following things. Do I have 2 quantities that scale in tandem? Okay, to break that down even more, first of all, am I in a scenario that has 2 quantities I can measure, like the number of eggs and the number of omelets, or the time I've been walking and the distance I've walked? 2 quantities I can measure. You need that. They can take on different values. They actually do in the scenario, like I've been walking for a while, and at different times I was different distance from my house. I really was different distances at different times. Or like the omelet scenario, I can imagine making different amounts of omelets and using different numbers of eggs. So either you can actually imagine having different values, or they actually do have different values in the scenario. And the values seem to have to depend on each other. For example, the number of eggs and the number of omelets do depend on each other. The more eggs, the more omelets. The time I walk from my house, the more time I spend walking, the further I've walked. So on, they depend on each other. But the key thing is you have 2 quantities you can measure that scale in tandem. If you double one quantity, the other quantity in that scenario must double as well. If you triple one quantity, the other quantity must triple. If you halve a quantity, the other quantity must halve. They must scale in tandem. And once you've got that, common sense will lead the way, just like eggs and omelets in the previous example did. All right, so let's just practice that. So the very classic example you probably see, I think, in practically every textbook is a pile of books. Here's a pile of books. Here's a scenario with a pile of books. And okay, right now I've just got a pile of books. And you can ask, well, what can I measure in this? Well, definitely the count of books. I don't know how many books I have here. Oh, I have 8 books there. And the classic thing to also measure is the height. Okay, so I've just identified 2 quantities I can measure: a count of books and a height in inches or centimeters or something, or light years, whatever you like, whatever height you want to do. Great. First one, yes, 2 quantities I can measure. They take on varying values. Well, not this particular scenario right now, but I can imagine having more books which have more height, or less books having shorter height and all the rest. Yes, they can take on varying values, at least in my mind. Great. They depend on each other. Absolutely. The more books I have, the higher it will be. If I want less height, I'll need less books. Yes, check, check, check. And the question now is common sense. You have to rely on real world experience now. If I double the number of books, will I get double the height? Common sense says yes. If I halve the number of books, will I get half the height? Common sense says yes. If I did 1/10 the number of books, maybe get to fractional books somehow, will I get 1/10 the height? You bet. 100-fold the number of books? Yes, 100-fold the height. Bingo. We're scaling in tandem. Beautiful, beautiful, beautiful. Now, if I rest this pile of books on the tabletop, which I think is probably about there on the camera, and said, okay, what about the count of books and the height from the ground? Yes, I still have 2 quantities I can measure, the count of books and the height from the ground. They vary, yes, more books, bigger height. They depend on each other, yep, more books, bigger height. But do they scale in tandem? If I double the number of books to here, have I doubled my height from the ground? No. No. Now I'm in a scenario that doesn't scale in tandem. I'm not going to be in a proportional relationship. So see, there's lots of subtleties here you have to think through. If I'm just measuring the height from the bottom book up, then the height of the stack is actually in a proportional relationship with the count of books. But height from the top of the stack to the ground, if the ground's way down there, which you can't see, different story. So you have to think through this. You actually have to think through this. But as soon as you recognize your scenario is scaling, as things scale in tandem, life will be then good. All right, so let's just practice that. For example, I'm to know that 1 inch matches 2.54 centimeters. I guess I'm doing unit conversion. All right, so 1 inch goes with 2.54 centimeters. So in some sense, I guess I am thinking of 2 quantities here, a length in inch and a length in centimeters. All right, they vary on each other. If I have more inches, I guess I've got more centimeters and vice versa. They depend on each other. Yep, they depend on each other. And do they scale in tandem? Now you have to rely here on your real world common sense. Yes, because if I double the number of inches, I would actually get double the number of inches, 5.08 centimeters. Or if I halve the number of inches, half an inch, I would get 1.27 centimeters. Yes, that makes perfect sense. In fact, I could do 1/10, I could do any factor I like. I can see that k inches, if I change this by factor k, we'll have to go 2.54 k inches, just relying on my real world experience. Yes, there's a proportional relationship, done, scaling in tandem. So if someone asked me how much is 100 centimeters, 1 meter, I could bounce around these numbers to get the number 100 to appear here and see what appears over yonder. Just use common sense, flail your way around through it. It'll be beautiful. Great. How about this one? I happen to know on my clothesline, one shirt takes 22 minutes to dry. All right. So, putting shirts on my clothesline outside, have a number of minutes to dry. I've got two quantities there that I can measure, count of shirts, number of minutes. They take on different values, and the question is, do these values vary? Yeah, I can change the number of shirts, you bet I can. And do they scale in tandem? So I have to take two shirts, double it. We always seem to double it. Everyone seems to go to doubles and halves, but it could be anything, triple, whatever. Two shirts, put them out on my line. What does my real world common sense say? How long will it take to dry? 22 minutes. Nope. This is not scaling in tandem. In fact, it's not really scaling at all. If I had 200 shirts, I'm sure it would still take 22 minutes, and so on. All right, so that's definitely not in a proportional relationship. This is kind of fun. Let's keep going. Suppose I said to you something like, well, let's do percentages. In a town, 720 people corresponds to 60% of the population. All right. So, have I got two quantities here? A count of people, and I guess another count of people, but now expressed as percentages. Okay, so they're very, closely related quantities here. If I double the number of people, if I did double the number of people, 1440 people, I guess that would be 120% of the population. Common sense tells me that. So I'm recognizing all these things are going on here. That count of people and count of people percent as a percentage is actually scaling in tandem. So if I want to know what 100% of the population was, like what's the count of people in the town, I might play with this line, 60, and divide everything by 6, only because I like the number 10%. This divided by 6 is something like 120, I think, people. So 10% is 120 people. Let's now multiply by 10, and I can now see that 1,200 people must be the full 100%. Bingo, I can play with it. I can play with it. Once I recognize things scale in tandem, I can answer any question I like. All right, this is fun. How about this one? How about this one? A map. A map. If I draw a map, oh, that's not a good pen. Don't draw a map in that pen. I guess let's say with the same green pen. All right, here's a map. And suppose it says 1:500 in some corner somewhere. Now, what does that mean? Well, if I say on the map, I measure the distance between this tree and the distance between this tree, and I see on the map that distance is corresponding to 2 centimeters, that means in real life, the actual distance between those two trees is going to be 500 times as big. It's going to be 1,000 centimeters, 10 meters. Okay, so there's scale drawing, a map. Is that something to do with a proportional relationship? Ooh. Well, the question is, do you have two quantities that you can measure? What are the two quantities that play here? And you think about it, I've got distances on the map and actual distances. Actual distances. Right now, I can say that 2 centimeters on map goes with, times 500, goes 1,000 centimeters in real life. Yes, they're the two quantities. Can they take on, I can measure them, yep, centimeters on a map, centimeters in real life. Take on varying values, yep, different distance on the map, different distance in real life. Have values that depend on each other, you bet they depend on each other. And do they scale in tandem? Why, yes. If I double the distance on the map, that corresponds to doubling the distance in real life. If I double the distance in real life, corresponds to doubling the distance on the map, they're scaling in tandem. Bingo. Scaled drawings are another scenario that leads to proportional relationship. Gotta love it. All right, what else? Do I write other things on my example? Yes. Constant rates. I think I mentioned this today. So here's me in my house. I'm going to walk directly east at 5 kilometers per hour. Constant rate of 5 kilometers per hour. Is that a scenario that could lead to an interesting proportional relationship? All right, so I need two quantities that I can measure. So what might I want to measure here? Well, I guess like I said earlier, I want to measure maybe how far I am away from my house and how long it took me to get there. Like how long I've been walking, how far away am I away? And clearly this thing is telling me something. If I'm going to get a constant rate of 5 kilometers an hour, my brain is now saying, okay, what does that mean in real life? That means, in 1 hour, I will have gone a distance of 5 kilometers. So 1 hour of time matches 5 kilometers of distance. And that makes sense. So now I've got two quantities I can measure, time in hours and distance in kilometers. They vary. Yes, the more time I can do different times, get different distances. They definitely depend on each other. And if I double the number of hours, it makes sense. My common world, real world experience says I would double the distance I go. If I triple the number of triple the distance, 333, I'd get 555, and so on. These are scaling in tandem. So actually, any scenario that talks about some sort of constant rate of some kind is really actually saying common sense. Constant rate, I bet I know one relationship and bet everything's going to scale in tandem. Beautiful, beautiful. Common sense. You have to love it. What else can I do? I know, unit conversion. We did unit currency exchange. I am to know that 13 Martian dollars, if you go to Mars, 13 Martian dollars corresponds to 10 US dollars. Ooh, okay. Is that a proportional relationship? Well, I've got two quantities, Martian dollars and US dollars, that I can measure. Yep, I can count how much is in my wallet. They take on varying values. You bet I spend money and my amount of money in my wallet varies. They definitely depend on each other. But do they scale in tandem? If I actually double the number of US dollars I have, make it 20 USD, will I get double the number of Martian dollars? You bet I will. Common sense tells me I would. It's all common sense in the end, and any question about converting Martian dollars to US dollars and vice versa is just going to follow from common sense. Whoa, this is it. This is it. The beauty of this subject is not all the fancy mathematics. The beauty is teaching kids to look at a scenario and decide whether they can actually do something meaningful with it. Can they recognize something scaling in tandem? Shirt drying doesn't do it. Other things don't do it. I'll give more examples in a slide after this video that you can play with and think about. Are they scaling in tandem or not? Because that's the real power, that's the real delight here of looking at a scenario and seeing what can I analyze it and use my common sense, my fabulous brain to make sense of and answer questions about it. This is the glory of this beautiful mathematics. Let's focus on this. This is the key. This is the key. All that other fancy math gets in the way. This is the key.